How's it going, everybody? Wanted to cover a new topic that, as of about a week and a half ago, I had heard about, but hadn't really dove into or really tested out before. I had understood the concept and the point of the technology, but I had never really tested it out. And for those of you that are in the SP world, you may be familiar with a term known as Unified MPLS or Seamless MPLS. And I struggled with the technology for a little while out of the gate because of the fact that I couldn't get it working the way that the implementation was described to me in a particular lab that I was following along with. And so I struggled, and I typically will keep going after something until I get it to work. So eventually I ended up having to make a couple of modifications to what I was doing, and I got it to work. So what you're looking at here in the topology is a relatively simplified single BGP autonomous system with multiple IGP domains inside of it. So not a confederation, but single AS, both running IPv4 unicast, IPv4 labeled unicast, as well as a VPN-v4 unicast. And so the goal, for those of you that are not familiar with Unified MPLS or Seamless MPLS, is basically it takes what people that are familiar with routing and switching from MPLS from the routing and switching track, basically what Unified MPLS is in a nutshell is take a normal design where you've got, let's assume that R1 and R3 currently are not on the topology, and you have R7, R8, R9, XR6, R5, and R6. So you take these middle 6 routers, and they're all joined to an OSPF domain, which is area 0. LDP is enabled between them, and everybody's hunky-dory. R7 can do a labeled trace route from R7 to R6 or XR6, and everything works, right? That's typically how MPLS is going to work in a very, very basic L3 VPN with no fancified bells and whistles or anything like that. Well, what that implies is if I wanted to scale out the MPLS core, so I wanted to add more points of presence, let's say maybe my service provider core is centralized. I've got a couple of devices in Chicago, a couple of devices in Milwaukee, and maybe a few devices in Minnesota and a couple in Iowa. I'm from the upper Midwest, so these are states that are surrounding Wisconsin, where I live. Well, that would work, and you could have, we'll say you own your own fiber between the connections, so you have your own DWDM set up between your points of presence, and let's assume that 5 and 6 are devices sitting between that. So let's, for the sake of argument, let's assume that Madison, Wisconsin, and Eau Claire, Wisconsin are routers 5 and 6. And you're running an IGP in between them for MPLS. You have your own autonomous system number, whatever that value might be. I'm using my CCIE number, so it's unique. And you interconnect all these devices through IGP. I don't care if it's OSPF or ISIS, but it needs to be a link state routing protocol. And the reason why it needs to be link state is because of you want to deploy things down the road like MPLS traffic engineering or RSVPTE. If you've been digging into MPLS like I've been, segment routing, things like that. All those things are really cool. The problem with that, though, is if I wanted to expand the network, let's say I want to get into the Dakotas, which is west of Minnesota, or I want to get into the Pacific or the Atlantic Northeast. I want to get into the Ohio River Valley, or I want to get into Pennsylvania, New York. I want to start spreading the network out that way. So I start spreading throughout the rest of the continental U.S. Well, I could start doing that, The problem with that, though, is the wider my IGP domain gets, the more routers you add to it, means the more time it's going to take for IGP to converge, more routes that have to be propagated. Even if you do fancy things like prefix suppression, and you only advertise the loopbacks into IGP, you're still going to have a lot of devices and stuff like that. Where Unified MPLS comes into play, you end up building a service provider core, and you use a specific IGP in the core. And you end up taking, and so in this case here, R7, R8, R5, R6, R9, and XR6 all have interfaces inside of OSPF Area 0. Now the process ID number is irrelevant, but what we end up doing is we end up taking the area border routers, so R7, R8, R9, and XR6. We end up taking these devices and we end up combining them in both IGP domains. So R7 borders is a border router for the Area 0 OSPF domain, but it's not trying to extend OSPF into another area. Now, from what I understand, I've been told it's possible to run a multi-area OSPF design. I've also been told it's supposed to be supported to run a multi-level ISIS design, the same type of setup. However, in my testing, I could not make the unified portion of MPLS work the way it had been described and demonstrated. I simply couldn't. I spent about 2.5 days on it trying to look up Cisco documentation and read through whatever it is that I was missing. Literally taking and building the exact same lab. So I took the Service Provider version 4 comprehensive guide, and I literally built the exact same topology that the author created. I built it, and I literally copy and pasted his configs into these routers. Still wouldn't work. I made sure the iOS versions were the same across the board. It wouldn't work for me. And at that point, when you take in what was shown in the book to be a functioning configuration, and you dump it in your routers, and it doesn't work, it's a little frustrating. So, and I'm not knocking the author at all. I am simply stating that when I tested it out, my results were different than his. And so, but here's one of the things. His labs were the only ones that were different than what other vendor labs had shown to make this type of solution work, as well as Cisco documentation. So I also looked up Unified MPLS labs. I Googled it. I found probably 3 or 4 different lab scenarios. A couple were Cisco's documentation-based labs. Others were a couple of blogs that I read. All of the Cisco and blog-related labs that I read all pointed towards using different IGPs. So OSPF, or some IGP in the core, and then another IGP on what would be the access. So the access is going to be these routers on the left-hand side and the right-hand side in the left or right box. So the big rectangle in the middle is OSPF. The square on the left and right are ISIS. So I was like, okay. So I took that design and I deployed it here. So I simplified. I had a much larger design. I was up to, I think, like 18 routers. It was ridiculous how big it was. It grew quite quickly because of the fact that I kept on adding. Like, I wonder if this is the issue. So, I wonder if it's licensing, or I wonder if it's this, or I wonder if it's that. So going back and forth, it was a lot of like, why is this not working? I don't get it. Debugs, and what's funny was it actually was working, right? I could do a trace route, an MPLS labeled trace route from R2 to R4. I would get a 2-label stack between R1 and R9 and R6, or XR6. And then it would be a 1-label stack from 9 to 3 and XR6 to 3, which is what you expect to see. But it was I wasn't seeing the 3 label stack between R1 and R7 through to R9. I wasn't seeing a 3 label stack, which is what I was expecting to see, because you're going to need a BGP label to jump over the core, right? So you're using this as a scaling technique, because then I could sit there and take and add more and more devices to this as I see fit. So the whole point of Unified MPLS is to be able to take and scale the network out as wide as you need it to be, and use one IGP and simply use BGP route reflection on the border routers, which is R7 and R8, R9, and XR6. You're using BGP route reflection, which implies it must be iBGP everywhere, one autonomous system, and you can scale it as wide as you want to go. I was like, well, that sounds like a pretty cool technology. Although I couldn't use ISIS level 2 in the core and ISIS level 1 in the access. It simply wouldn't work. I couldn't get it to trigger. I could get the BGP labels to trigger. I could get all that to propagate, but I couldn't get the data plane to show multiple labels, and I couldn't figure out why. So I chalked it up to I was doing something wrong, but I couldn't figure out what it was that I was doing wrong. So I said, okay, you know what? Because of the fact that I'm studying for my the SPCCIE, I'm planning on taking the written here in a couple of months at Cisco Live. It's something that I really, really wanted to get working so I could sit there and verify on a hop-by-hop basis and understand what's really going on. So a new technology that I typically will do that just because of the fact that I'm kind of I'm OCD about that type of stuff. So I said, all right, well, let me go build this lab, and then I took and I used a combination of multiple blogs and Cisco documentation to build what I've got going on now. And I'm using OSPF in the core, ISIS on the access edges, and it is working. I have a 3 label stack in the core, and I'll show you what that looks like. So what ends up happening here, for those of you that are not familiar with this, is you are using, let me go ahead and let me start to kind of draw out here what is operationally happening so that everybody follows. In the description below, you should see a couple of links in there to a blog post that I recently did yesterday that points to kind of walks you logically through what's going on here, because it's one of those things where if you've never dealt with it or you've never played with it, it's one of those things that it can be a little tricky to understand. So what you're doing here, and this is where it gets a little interesting, is you're running LDP here in this guy, you're running LDP here, and you're running LDP here. That's fine. That builds label switch paths between these devices, and then these devices, right? And there's obviously LDP here as well. What that also does is when you're setting up your iBGP pairings, this connection here, this is iBGP. This is iBGP as well. And so what ends up happening is you add the IPv4 send label command on R7, and that's going down towards R1 as well as the pairing to R9. So R7 and to R9 and R7 to R1, you're using the send label command, which is this adding a BGP label, which technically is not 100% true. BGP is being added, the labeled capability is being exchanged, but you're actually pulling a label from the global label pool that all of the label mechanisms pull from. So you have a label space, a global label space, an iOS, the label table, and that is a 20-bit field. That's how big the label space is. If you look at a Wireshark capture, it's 20 bits, which gives you right about 1 million labels. So regardless of what you do, whenever you configure it, you end up going out and you allocate your LDP labels, your RSVPTE labels, your BGP labels all come from the same address or label pool, right? and they are allocated in an ascending order, so from lowest to highest. So the only difference is when you're dealing with segment routing in newer versions of iOS XE and segment routing in iOS XR. In iOS XR, there's a dedicated label space, 16,000 through 24,000, which is why if you look at what the LDP label space is, that's why you see LDP-based labels or anything that's any labels that are allocated from the global label block starts off at 24,000 because the first 8,000, so 16,000 through 24,000, are allocated for segment routing. So we end up taking that logic. So you send label. Now the connection down to R1 is a route reflector. And on R7, for the connection to R1, you type in the command next hop self all, which tells R7 you're going to be updating the next hop for both eBGP learned routes and iBGP learned routes. Where normally next hop self is only for eBGP learned routes, you're going to tell the iBGP neighbor, use me as your next hop. Where eBGP, it's leveraged as well. Documentation states to use next hop self all. I use that command. I didn't test it without using next hop self all. I'll let you guys play around with that. So then when I do that, I form a pairing with R7 forms a pairing with R9 and XR6, and so does R8. So R8 forms a pairing with these guys as well, and R9 and XR6 do the same thing. So you end up forming a bunch of pairings like this. So it's a full mesh, essentially, right? So you end up getting all of that working. Then R7 and R8 form an iBGP pairing down to R1. Same thing with R9 and XR6 to R3. So these guys here are route reflectors. Now, there's a unique thing that needs to be done on XR6, or XR in general. And it's called the iBGP policy out enforce modifications. This is done globally on the box, and that takes any updates that are received and allows them to be updated. Now, because normally next hop self is not something that you would use for like a route reflection type of configuration. So it applies any updates you're going to send. It enforces the modification rather than just bypassing it. So the area border routers, R7, R8, R9, XR6, are route reflectors. And they are route reflecting down towards the PE router, but not route reflecting towards the remote area border router. So that's just a simple labeled BGP. That's basically what it is. Now XR has a address family called labeled unicast, and you use that. You don't need to enable that globally because it's a subset of IPv4 unicast. You can simply go in and use the labeled unicast address family and only activate IPv4 unicast globally, and then it goes ahead and informs. Now I've already done a blog post on that, so I'm already pretty familiar with the walkthrough. So let's go ahead and take a look at a flow. So let's go to R2, and here I've got a trace route that I did a little while ago. And you see that I'm trying to get from router 2, which is on the far left, to router 4's loopback, which is 192.0.2.4. I'm sourcing off of R2's loopback, and I'm saying don't do a DNS lookup for the traces. So I'm saying, which implies that R2 and R4 must be exchanging routes with each other and learning them through the MPLS core in order for the devices to come up. So I have an outbound pass or a path towards R1, and this is where the label values start to come into play. Now this is the first labeled path, and this gets me from R1 to R8. Now I'm taking this path because it's the newer of the two. I'm sorry, the older of the two. Because I actually disabled R9 after I got it working. I got XR6 up and running, and then I re-enabled R9, but it still chooses the R6 path because of the fact that it's just the older the older of the two paths. So what ends up happening now is I take a labeled path. So to get to R8, I take this path. Now 28 is the BGP label that's associated here, and 22 is the VPN v4 label. So if I'm not sure how that comes into play, I go to R1, I do a show BGP IPv4 unicast labels, and I see to get to R3 towards going through R8, I use outgoing label 28, which matches what I have here. So I know this is my BGP learned label. Even though it comes from the same label space as the LDP label range, it's BGP is the one that allocated it. Now, I use label 22. This is the VPN v4 label. So I go to R1 and I do a show BGP VPN v4 unicast all for the 192.0.2.3/32. I'm sorry, 4. If you look right here, because I learned this route from R3, because R3 is the one that advertised it to me, I have outbound label 22, which means that if we go to R3 and we do a show BGP, we'll see that label 22 is a local label that was allocated for R4's loopback. So because we've learned that, R3 will propagate that to R1. You'll have to pardon the dog, it's barking behind me. So that this VPN label was allocated by R3 to get to R4's loopback, but it was propagated towards R1 as the VPN label. So we take that. So then when we say, okay, if we're going to do a show IP route for 192.0.2.8, how do we get there? Well, right now it's telling me to go out the local connection. And what ends up happening now, if we do a show IP set for the same output, this is where we got to go next. But you'll notice it's not a labeled peering because it's directly connected. If we do a show MPLS forwarding table for router 8's loopback, we end up getting what they call as a penultimate hop pop. So we're actually getting, if we do a show MPLS LDP bindings for neighbor 192.0.2.8, we should get an implicit null for anything going towards router 8's loopback. And as soon as I find it, right here. So for router 8's loopback, right here, we get a remote binding of implicit null. Now if I go in here and I think I can go detail. This should be, let's see, does it give me a specified label binding? It doesn't, but I haven't checked in a while, but the last time I verified this was label 3. So label 3 indicates implicit null or penultimate hop pop, which R8 is saying, R1, I don't want you to allocate a label, or I don't want you to use a label to get to me. I want you to go ahead and forward to me via native IP. So, but this is the end of that label switch path. And how do we know that? Well, if we do a show BGP IPv4 unicast summary, I have an IPv4 BGP peering with that to this IP address. Your LDP neighbor's loopback should also be your BGP next hop. In this particular case, it is. So, because R8's loopback is used as the router ID for IGP or for LDP, excuse me, what ends up happening is I end up pointing towards the loopback of R8 for my BGP peering, because R1 can get there through R8 or through R7 through ISIS routing. It's also my BGP next hop, because when I go to configure BGP, show run section BGP, I point to R8's loopback and I say, you know what, let's go ahead and set the update source as loopback 0, which is also my R1's router ID, which is R8's next hop to get to R1. So that's how the label switch path here terminates on R8. And it's not end-to-end to get to R3, which is why Unified MPLS is needed, because your LSP is not end-to-end here. If I do a trace route to 192.0.2.3, sourcing from loopback 0 numerically, I don't use the same labels. If I did use the same label, I would see it would be a solid LSP, but because of the fact that I have an IGP domain here that's split in half, I also have another one over here that's split. So because of that split, because you have two different disjointed, your IGP is disjointed by another IGP sitting in between them, you need some other mechanism to bridge that gap. So in this particular case here, we use the this is the labels that XR6 is allocated, because I can tell based off the label value. And then you also have the LDP label that you're going to use to get to 5 and to get to 6. But that's because of the fact that it's technically not a end-to-end label switch path. So we're using a BGP label to get over the top. And how I know that is because 20 is going to be used to get to XR6, and XR6 is going to be advertising 24,000 to get to R3. So you might say, how do I know that? Well, I'm glad you asked. We come over here to R8, we do a show IP route to 192.2.0.3, hit the enter key. So I use label value 24,000, that's how we get to R3. But here's the thing. Now I know how to get to R3, but I need to know how to get there from where I'm at. So R8 and XR6 are forming a peering, which means that this is my next hop. If I do a show IP route for that guy, my label here, it doesn't actually show up here, right? I have to go say show IP ceph for this particular value, and this one says label 20. Then we go back up to here on R1, we look right here, look at what we have here, label 20 and 24,000. So we go back to R8 and we say, okay, R8, we look here, we see label 20 gets us to XR6, or yeah, XR6, and label 24,000 gets us to R3. We do a show BGP IPv4 unicast labels, we'll see that we have 28,000 and 24,000. Or I'm sorry, 28 and 40,000, or 24,000. So what that means is, if we look back here for our BGP labels, 28 is incoming from is the incoming label from 23, or to get to R3 from R1. So even though it says the incoming, but see, notice how this is laid out. The in label here is this one. So we see 28. The outgoing label is 24,000. That gets us to XR or router 3, but I have to pass through XR6 before I can get there. So I need to know what that label value is, and that's how we know this. We do a show IP ceph for 3. We know we're using a 2-label stack, 24,000 and 20. And again, 20 gets us to XR6, and 24,000 gets us to, and 24,000 gets us to router 3. So we end up taking a 2-label stack. Now we get to R5, and R5 is not going to show us anything unique. Show MPLS forwarding table. We do a show IP route. We look in here. We're going to see the loopback of XR6. So we come in here and we say, okay, what is this value here? We're going to see that nothing shows up. It's an OSPF learned route. Show IP ceph for the same prefix. And it says using label 18. If we go back over here, we do see a label 18, right? But that's the LDP label. This is the BGP label. This is the LDP label. And if we go through here, the BGP label stays the same. I have to be kind of careful here, because when we look at this, it's technically LDP and BGP. Because BGP is where we're pointing ourselves to. They all come from the same label space. Just who's allocating them is the differentiator here. And all we're doing is we're using this label here to get us in the core, which is LDP learned and advertised and allocated. 24,000 gets us to where we got to go there. But if we look in the core, we look in here, we don't see R3, right? If I come in here and do a show IP ceph for .3, network's not in table, right? And that's because of the fact that we haven't advertised the provider edge routers into the core domain. We're just using the area border routers to propagate a little bit of routing. That's why you see in the show IP route command, that's why you see these OSPF routes here. 7, 8, 9, and 16 are here and propagating routes. So what we want to do now is we want to take a look at the actual, to finish up the traces here. So R6 is the same way. So it's really no different than R5. We have a next hop of XR6. And so now let's go to XR6 directly and log into him. Now this is XR6 running 6.0 code, which is what you will be tested on in the CCIE lab. So we do a show route for 192.0.2.3. It's locally adjacent here. Show Ceph for 192.0.2.3. And we end up getting a label imposed with implicit null, which means that it's labeled 3, and we're going to pop the label. So that's end to end how we're doing this. So now that we understand the logic and the workflow, let's take a look at some of the basic config here. So on R7, for instance, if we take a look and do a show run section BGP, we're going to see there's a lot. So I'm going to go full screen here and break this down. So what we end up having is we pair with R1, R9. I have some extra stuff in here from other testing, but then we pair with XR6. So that's all we really need to pair with. I actually don't need XR3 in here, but it's there anyway. With R1, we activate the adjacency. We tell, we configure it as a route reflector client. We set next hop self all for both iBGP and eBGP updates, and we send label. So that's one of the things we need to check out. Do a show BGP IPv4 unicast neighbor 192.0.2.1 and hit the enter key. If you look right here, you're going to see IPv4 MPLS label capability is advertised and received. If it's advertised but not received, or received and not advertised, that is a bad sign, because then you're not actually allocating BGP labels. We do a show BGP IPv4 unicast labels. We can see the labels that we're allocating. 30 and going towards R9, it's 30 and 17, and we have, this is what's coming from R1, and then what we will be using to get to XR6 and R9 respectively. So that's basically how that comes into play. So that's just some of the specifics to how that works. And if we do, and that's really all there really is to it. I mean, fortunately there's no magic really with Unified MPLS. It's the architecture that you're trying to achieve with the design that you've been given. So if you have a situation where you've been tossed a design like this, a multi-area OSPF, or sorry, a multi-area OSPF or a multi-level ISIS design, you don't have to worry about this. Now, let me just be for full transparency. When I tested it out on an ISIS level 2 here in the core, and ISIS level 1 on the left and on the right, I did not get a 3-label stack. I got a 2-label stack. So I got LDP, I got a transport label and a VPN label. I knew I was running into problems when I would see a blog post showing a 3rd label in the stack. So, and just to show you what that looks like again, we have VPN label here. We have BGP label getting us over the core from R8 to XR6. And then we have the LDP label. Now, here's the thing that's interesting. There's been some debate that, and documentation is not clear, so I'm interpreting what I'm reading and trying to make the best of it, where you have VPN labels always on the bottom. The one that never changes is always the VPN label. Unless you're changing label switch paths, like you would be in like an inner AS option B, that's a different situation. That would be a different different VPN label, because it's 3 different. You've got an LSP from ingress PE to AS and ASBR, and then you have another label switch path between the 2 ASBRs, and then you have another LSP from the ingress ASBR to the egress PE router. Now, because of the fact that these values all come from the global label stack, they're technically all LDP, right? The only difference is how they're being allocated. So when I look at this on an R7 type of situation, I see this right here as the BGP label, and I look back at R2 and I see 18, this is LDP. So I see LDP, BGP, VPN v4. That's how I, like when I'm reading through this, and I don't think anybody's going to argue that point with me. Well, I shouldn't say argue, debate that, because it's literally how the allocation happens. So VPN v4 allocates this label, BGP allocates this label to get me over the core from R8 to XR6, and this label here gets me through the core. So it gets me R5 to R6. This is actually the R6 label. I can tell based off the IP address, this is R6. R5 is 20. So 24,000 is the label that's been allocated to get me over the core. So this is the BGP label. Okay. So now that's layer 3 VPN. I also have layer 2 VPN, and it is supported, I think, multicast as well, but I have not tested that out yet. So what I haven't done is on R1, I'm going to go over here and take a look at this and see, do a show xconnect all and hit the enter key. According to this, I do have a pseudo wire up and running, and all I did is a show run interface gig 2. I just have a simple xconnect pointing to towards R3 for the virtual circuit ID of 24, encapsulation is MPLS. A very, very basic layer 2 VPN. I do plan on testing this, adding more routers. So I'll end up taking and having more access edges. So 3 or 4 more routers per edge, and then a couple more routers in the core so that I can extend the capability, and doing VPLS, HVPLS, so on and so forth. So if I go to R2 and I do a show IP interface brief, and I look here, I have an IP address of 10.2.4.2, R4 is 10.2.4.4. So if I ping 10.2.4.4, will I get a response back in? And I do. If I do a trace route to 10.2.4.4, which is actually going to be funny about this, for those of you that know what I'm doing, it's going to appear as directly connected. So if I come up here and I do this ping, or repeat it, like say 10,000 times, and then I go over here to R2, or I'm sorry, R1, to show MPLS forwarding table, what you're going to see is this 30,996, that doesn't actually increase, which is kind of funny because of how it's actually, now it does. Just the timer values are a little slow for the calculation, but we can tell layer 2 VPN is working because this number has increased, and we're almost done with our ping, but we know that. So here's the other test you can do. This is how I normally test it. Is I go to global config, I type in router EIGRP 1, I type in network of 10.2.4.2 0.0.0.0 and hit the enter key. And I go to R4 and I go to global config, router EIGRP 1, network of 10.2.4.4 0.0.0.0 and hit the enter key. Now if I form an EIGRP adjacency over that circuit, I know layer 2 VPN is working. That's usually how I go about and test it, because this way here, as I'm going through, I can arbitrarily watch it. So what you see me do in this video is walk you through the logic of Unified MPLS. I've also then explained to you the packet walkthrough and how the labels are allocated and the label stack and how that comes into play, as well as going through and doing a layer 3 VPN walkthrough, and then doing the demo, the setup for layer 2 VPN, which is a simple xconnect, and going from there. And this is this would be a port-based atom, but so we have an EIGRP adjacency going back and forth between them. So if we come back over here, or back to R1, hit the up arrow, we're going to see that number increment over a period of time. And that's because of the fact that there's EIGRP hellos going back and forth, and you know, you had to account for that data going back and forth. So No, XR6 with 6.0 code does not support layer 2 VPN in the data plane. And I have found that for multicast on 6.0 code is not supported either in the data plane. The blog post that I did where I tested out multicast, I had to actually use a 5.3 image for testing out multicast. That's just been my testing. And I've actually been pretty involved, semi-involved, with the Cisco Learning Network CCISP study group. And I've gotten some feedback from the program manager about what's going to get tested on and stuff like that. So I've got a checklist of things left. So beyond Unified MPLS, doing layer 3 and layer 2 VPN, the only thing that I haven't done is multicast VPN. I've tested Lisp. I actually had Lisp working. Oh, it's currently working in one of my customers. I also deployed OTV in a 3-site design. I did VXLAN. I've also done, now these are technically non-SP topics. Lisp is on the blueprint as it describes, so you're not going to get tested on that. DMVPN I've been doing for years. I've deployed that hundreds of times. So beyond this, the last things that I have to test out, because I want to test it out, is going to be MGRE L3 VPN. So taking basically DMVPN and running MPLS over the top of it. That's one variation of it anyway. I keep looking up at, I have a checklist of things that I have left to cover. That's why I keep looking off camera. And beyond that, I want to go through and test out carrier supporting carrier again, the inter-AS L3 and L2 VPN concepts again, and then I believe that should be just about it. Those are the major topics. I have some other that are more service related stuff like advanced BGP, doing things like route target constraints and stuff like that. I've got to go through that, but I wanted to cover some topics that I had never hit before, and go from there. So now that I've gotten this topic out of the way, I'm going to actually take, and I've got routers 1 through 9 rolled out here, and I've got 5 other XR boxes that I have yet to pull out and set up in here, plus another, what is it, 6 CSRs. What I will end up doing is this topology will actually grow a little bit. The core is going to grow 1, 2, so I should be adding 4 more boxes here, 1 more CSR, 3 XR boxes. This guy over here, the left IGP domain, that'll grow by 2. The right domain will grow by 2, which this will be, that'll put me at 10. And then we actually grab this out as I'm thinking about it here. XR1, XR2, and XR3. XR3. And then I'll have R11 and XR2 or XR4. And then I'll do R12 and XR5 over here. And then I'm going to use R2, R4, and then 13, 14, and 15 as branch sites and roll some stuff out that way so I can test carrier supporting carrier, MGRE L3 VPN, and I think that'll be about it. I want to test out OTV one more time. I want to do a video on OTV. I want to do a video on Lisp, stuff like that. If you want to see more of the configuration, I will put a link to the blog post that basically I took a copy and paste of what the configs are in this lab here, and I'll drop it in the link below, in the description below, so you guys will be able to see that. And then once that's done, there are it's not a lot of. I need to do kind of a multicast deep dive again and an IPv6 deep dive. There's some topics like I'm going back to Nick's book and reading up because he did a really good job of laying stuff out. IPv6 multicast, and then I'll round out the BGP stuff. So I'll actually I have a couple more things to test just to go through and do a blog on it and whatnot. I did some stuff a long time ago, but it's been probably a year since I've covered carrier supporting carrier. So I'm just trying to do a quick refresher on how it works. Not doing anything fancy. There's some stuff that I've left out option-wise, but I'll be covering that when we get into CCIE for service provider, which I'm ramping up for that currently. But I've got some stuff that I need to do. I need to finish the CCNP service provider workbooks. I know I had mentioned both in a newsletter and in some videos and whatnot that I was going to do workbook videos. I think I'm just going to focus on workbooks and get them done, so that when it comes time to doing the videos, it's just banging them out and getting them done, because there's a lot of theory that I need to cover that you won't get in the workbook. So that's pretty much what I got going on. So it's going to be a busy few months, but that's okay, because that's actually kind of how I prefer it to be, and we'll go from there. So I'm hoping to get the NP workbooks done by, I have a target. I want to be done by the time I go to Cisco Live, but because I'm adding material to them. So for instance, I already did route, so that workbook is available currently. I'll be adding in advanced route. I'll be covering OTB, Lisp, DNVPN, NAT, IPSLA, and anything that's MPLS specific, I'll be adding that to the MPLS specific videos. So traffic engineering, and then what do you call it? I'm having a brain fart at the moment. Like Unified MPLS, I'll cover that again in NP. We're bringing a lot of topics from CCIE down to CCNP as a transition for you guys. You won't get tested on anything that's outside the blueprint, but at least it'll be there, so that if Cisco ever does upgrade or update the CCNP service provider exams, you'll see the newer technologies already covered. Anything that isn't covered, I'll just add material for it. But like I said, I feel I'm getting more and more comfortable and more confident in these technologies. It's just a matter of expanding on that. I have some traffic engineering and some fast reroute to cover yet, stuff like that. But it's all, to me, it's all minimal stuff. But that's pretty much it, guys. You'll see more of this type of stuff coming out, and the workbooks. That's why I'm usually silent, is because the fact that I'm doing workbook development, and I want to do a good job for you guys on those and stuff like that. I actually had a comment on the workbooks. I got like a comment like a week ago that one of the labs is very vague on what how to configure something, and I kind of do that intentionally because I want you to kind of use your imagination, to get stuff working. I don't want to dictate to you anything. I want you to, if you've already, I haven't done the videos for them yet, so it's kind of misleading at the moment. But for instance, for ISIS is a little bit more strict than OSPF is to get working. So like for instance, if you take ISIS, you have to configure a net address, which is basically the router ID, and stuff like that. And I don't dictate any of that stuff to you, but what I do is I give you the freedom to be able to do whatever you want and go from there. If you can get it basically up and working, you're okay. I just will give you an example of how I deployed it and stuff like that. And I get some labs are more complicated than others and have more restrictions and have more specifics that you have to meet, and that's only specific to that particular lab at the time. But it is what it is. So without any further ado, that's pretty much what I have for you guys. Again, I'd like to thank everybody for their continued support. You guys have been awesome in, keeping up with me and stuff like that. I'm going to try to keep putting out more and more content as I go along. If you have any questions, or if you are new here, bang that subscribe button. Until next time, guys, thank you so much, and I'll catch you guys in the next video.